When current flows through a wire, it follows the path of least resistance. Charges move neatly end to end in a straightforward line. But if you bring a magnet close to that wire, the clean forward flow breaks down. In 1879, a physicist named Edwin Hall was attempting to calculate exactly how magnetic fields interacted with electrical flow when he noticed this contradiction. Hall set up a flat, thin strip of gold, ran a steady current straight through it, and placed it perfectly perpendicular between the poles of a heavy horseshoe magnet. Under those specific conditions, his instruments picked up a quiet, completely unexpected measurement. A small voltage was forming sideways, across the width of the gold strip, at a direct right angle to the current itself. The data scaled cleanly. If Hall doubled the current, the sideways voltage doubled. If he physically flipped the magnet, the voltage instantly flipped direction. Magnetic fields do not do work on charges. They cannot speed them up or push them along a new path. There was no obvious mechanical reason for this lateral energy to exist. Inside the metal, electrons drift smoothly. Introduce a perpendicular magnetic field, and they experience a sideways force, drifting off course. They crowd one edge, making it negative, leaving the opposite positive. This charge separation generates a secondary electric field, pushing back against the magnetic deflection. Eventually, the system hits a precise mechanical balance point. The lateral push from the magnet and the aggressive pushback from the accumulated charge become perfectly equal. At that exact moment, the sideways drift halts. The reading on Hall's instruments did not capture charges in motion. It measured the tension of charges trying to move sideways, piling up, and being violently stopped. Hall repeated the exact same experiment, maintaining the identical current and magnetic field, but he swapped the flat gold strip for a completely different metal. In the new material, the sideways voltage violently flipped its polarity. Logically, this shouldn't happen. Because electrons are universally negative, the lateral buildup should reliably happen on the exact same side of the strip, regardless of the metal being tested. Inside these specific metals, the effective charge carriers act like positive particles. They are physical voids, gaps in the electron structure. Behaving mathematically as positive charges, the magnetic field deflects them toward the opposite edge. By simply measuring a voltage that refused to move, Hall accidentally mapped the hidden internal behavior of subatomic charge carriers, decades before quantum mechanics existed to formalize it. For the next century, the sideways voltage scaled smoothly. Double the current or double the field, and the measurement rose in a perfectly predictable line. But drop the temperature down to near absolute zero and apply massive, sustained magnetic pressure to the metal, and that smooth scaling shatters. This chart captures the exact physical breakdown. Instead of following the expected smooth, diagonal line, the voltage jumps. It locks into rigid, discrete steps, completely refusing to take on any intermediate values in between. This, right here, is the quantum Hall effect. Under these extreme conditions, electrical resistance becomes quantized, locked into exact repeating fractions of universal constants. A macroscopic sideways drift inside a basic piece of wire ends up mapping the mathematical step-by-step grid of the quantum universe. You do not need a supercooled laboratory or extreme magnetic pressure to rely on this physics. The tension of blocked electrical drift operates quietly inside the hardware you use every day. Microscopic Hall sensors sit embedded in your phone, reading tiny fluctuations in the Earth's magnetic fields to determine your orientation instantly. In modern vehicles, these identical sensors use sideways voltage readouts to safely measure wheel speed and engine timing without any physical parts grinding together. And heavy industry monitors massive, incredibly dangerous power currents safely from a distance, purely by reading the lateral tension built up inside the wires. We usually measure physical forces by the movement they create, but forces also operate as a hidden pressure. They create canceled-out directions, tensions that quietly build up just enough resistance to leave a measurable trace on the world, but never quite enough to break free.